It should be recording now. Okay, welcome everyone to season 5. We're happy to see so many people here. So we're starting off with a talk by Giacomo from the University of Zurich and IBM, who will be talking about fully anonymous ring signatures from quaternions and isogenies. So Giacomo, the floor is yours.
Thanks for the presentation. And hi all. Yeah, I will present this joint work with Ifu and Antona. And in particular, I will focus, like in this work, we presented two different ring signature, one like of linear size based on SQISign and another one based on GPS signature scheme that is logarithmic size. And in particular, here we will focus on the first one, the one based on SQISign. And we'll try to see what are the problems, what are the solutions, and the involved protocol that we focus on. And also, I will try to like not do a boring introduction at the start of all the stuff I need, but introduce them on the fly when I need them. So if at some point someone is like confused and think like that someone should have been introduced more or has not been introduced at all, feel free to stop me and ask any question, and yeah, I will be more than happy to try and reply. So let's start from our objective that are like ring signature, and our goal like is to get a signature scheme, a cryptographic scheme, in which given a set of user and a document, I can produce something that will show that I know essentially, sorry, that one of these user is essentially approving this document. That means essentially that given the set of public key associated to this user, the blue, the green, and the purple one, and if I know just one secret key associated to one of them, I can produce a valid signature for this ring or this document that can be verified knowing the signature, the document, and only the ring. And this signature, like this key, clearly should be like unforgeable in the sense that without no one of the secret key, I should not be able to produce a valid signature, and also anonymous in the sense that given the ring, the document, the signature, I should not be able to understand which one of the particular users signed it. So which one of the particular secret key was involved in the signature procedure. And then clearly, like, I also want it to be efficient, to be like practical, something that can be used in a real situation. Okay, so since we will focus on SQISign, that is an identification protocol, I will try to give another look on ring signature, but this time focusing more on like an identification protocol point of view. So suppose that you have a relation, an NP relation, which I have like a statement that in this case will be X, and a witness that is bool. For example, in the SQISign case, that the statement is a super singular analytic curve, and the witness is essentially the endomorphism ring of this curve, so some kind of information, secret information associated to it. And then I want to define on this relation an identification protocol that will allow me to show that I know this witness. And from it, it's like a super standard construction. I can apply a fiat Schmidt transform, make it non-interactive, and get a digital signature. This is something I think super well known, a lot like used from several decades. But like with this in mind, we define a ring signature as essentially an identification protocol for a special kind of relation that is an OR relation. That given an NP relation R, essentially an OR relation is a relation in which I have like n statement, x1, x2, xn, and I know only one index, sorry, one witness for this statement. And essentially given a proof identification protocol for this relation, I can define what is called like an OR proof for this relation. We say it OR proof because essentially proving that or I know witness one, or I know witness two, or I know etc. up to witness n. And there are like several ways like let's say standard way to get from a unification protocol for R to an OR proof for R that are like like sequential parallel logarithmic with different characteristics and different requirement on OR proof. And then if I have this kind of OR proof, I can make it non-interactive, and I get essentially a ring signature because I'm showing, as in like in the Fiat-Shamir case, I show that I know the witness and I incorporate the message in it. Here I show that I know one of the witness, that is one of the secret key, and I can incorporate clearly the message just by like stuffing inside every action evaluation. Okay, in particular, for SQISign, for this construction, Erebor will focus on a particular kind of OR proof, that are sequential OR proof, that were introduced already like 2 decades ago by Masuki, Okubo, and Suzuki. Essentially, this framework allow, given like an injection protocol that satisfies some particular relation properties, in other words, that is a sigma protocol, stimulatable in probabilistic polynomial time, and with special unspecified zero-knowledge property, I can immediately get a linear ring signature. So now I will go more into detail on what is written here. So first of all, a sigma protocol is just an unification protocol in which like a prover tries to convince a verifier that knows a witness with like a minimal number of rounds. It is essentially 3 rounds. And then like our favorite example of unification protocol is the SQISign unification protocol, in which like our statement is the super-singularity curve, APK in this case. And our witness is a secret isogeny that will link this public key to another curve on which we know in the Morphin's ring. And like in unification protocol, the first step is what we always call the commitment, in which I send some kind of information to the verifier. In this case, I will send to generate a commitment, I will generate a random isogeny that I will keep secret. And then I will fix as a commitment the codomain of this isogeny. Then I will receive a challenge. This one is for the verifier. It is like a string of random coins. And from this random coin, I define in a deterministic way a challenge isogeny and a challenge curve that is the codomain of this isogeny. And then to actually show that I know the secret, that I can, let's say, that I can control this public key, I need to show a response that in the SQISign case is essentially an isogeny between the public key and the challenge curve. Clearly, we know one possible isogeny, that is the path given by the secret key, the commitment, and the challenge. But this one is not an option because otherwise this will leak the secret key. But there are several ways to overcome this. For example, in SQISign HD, what I do, okay, they know one possible path. That means that essentially they know all the possible path. And these possible paths are contained in lattices, 4-dimensional lattices. So they just like, okay, I'm showing it as simple, but like clearly it's more difficult than what I say. But the core idea is just, okay, apply LLL, get a short path, and use the Canis lemma to represent it. Essentially use the attack on CDH to represent this short path. Otherwise, if we are not allowed or like we don't want to go in another dimension, we also have like the original SQISign, the one based on KLPT, in which essentially I take this secret path and I transform it in another path that is smooth, that is like a sequence of 2 isogeny of degree 2, that is like very long, but at some point it will reach the challenge curve. And then I will send it as a challenge. Okay, so this one is a Sigma protocol. Now I need it to be like honest verified zero knowledge. What does it mean? It means that essentially, without the knowledge of the secret key, I can generate a transcript that is undistinguishable from one generated during an actual exchange. And like, for example, for SQISign HD, the strategy is quite simple and quite nice. Essentially, suppose that you have an oracle that will pop up a random isogeny of the degree similar to the one that is involved in the SQISign HD protocol. Use it as a response. From the domain of this isogeny, you get the challenge curve. From it, you define a challenge, the dual of the challenge isogeny. And from the codomain of this dual, you get the commitment curve. And then you send the commitment, the challenge, that is the dual of this isogeny, and the response. And you actually have like, something that, under very mild assumption, is undistinguishable from a valid response. However, even if this one is satisfied the honest verifies the knowledge property, is not simulatable in probabilistic polynomial time, since here we have an oracle that will pop up an high degree isogeny that, like, as of now, we don't know how to actually implement this in polynomial time, probabilistic polynomial time. So we have to use, in this case, the old SQISign, the one based on KLPT. And essentially, we generate, in this case, the response is just a long isogeny, a long chain of two isogenies. And it's something that we can actually generate in polynomial time, very easy. We know how to do that in a procedure essentially similar to the CCL hash function. Then from this one, we get in the same way the challenge curve, and we simulate both the challenge isogeny and the commitment isogeny in the same way. And this transcript that I get is undistinguishable from valid transcript, but I need to add like a computational assumption that is not so clear, at least of now. Clearly, there is no attack, but it's not as weak as the one proposed for the SQISign HD. But also, we are not finished yet because there is another problem. We need the protocol to be simulatable, honest verified zero knowledge, but also special honest verified zero knowledge. That means that I essentially can run the simulation starting from a particular challenge. And since here the challenge is an isogeny that starts from the commitment, like we really don't know neither how to create the commitment and neither how to create the response, but this would require to link a random curve from to another public curve. And so we need to modify the protocol a bit, but this is actually possible. And the idea is quite simple. So instead of like, we start as the same. So we generate the secret key starting from, the public key starting from in0. We generate the commitment again starting from in0. But now the challenge isogeny after the retrieval of the commitment will be starting from the public key. Like this one, when we are like in practice, is not a problem because like the point is that in efficient transform, I need to get the challenge isogeny as a result of the hash of the commitment. So like even if like the challenge isogeny doesn't start from the commitment, it still will depend strongly on the commitment. And then when I need to get the response, I will still consider the path that this time will pass before the dual of the commitment isogeny and then through the secret key and the challenge. And I will run the KLPT algorithm, this time using the psi as a link, as a way to show to use the endomorphism ring of the commitment curve. And this also implies that I need like to have something efficient, that this psi it's very short, because usually like we would like instantiate SQISign with a short secret isogeny, while here I need to instantiate it with a short commitment isogeny. But then like everything is the same. I can just run the algorithm in the same way, and I will get the response isogeny. This is again sound. In fact, like if I can answer two different challenges from the same commitment, it actually means that I know like these two different paths, these two secret paths going from the commitment curve to the public key curve. And like if both these two are cyclic, clearly, and their composition is an endomorphism, that is something that if you don't really know the endomorphism ring, you shouldn't be able to show. And like this stuff wasn't done initially for SQISign for several reasons. But for example, just to mention, if you look at SQISign HD West, for example, they will use this kind of protocol instead of the old one, starting with the challenge starting from the commitment. However, even if there are some like little disadvantages, that is essentially the shortness of the commitment curve for designing KLPT, sorry, for the SQISign KLPT version. Still, there is the advantage that now I can actually run the simulation starting from the challenge. In fact, given any challenge isogeny, phi challenge, and the challenge curve, I can just generate the response by working at random from the curve, the challenge curve. And the only problem is that I don't only have the computational assumption of SQISign, but also the problem that this commitment curve technically is linked to zero by a short psi. So there is an even stronger computational assumption. However, we are paying this price to get something that can simulate a valid transcript just starting from the challenge. So we have this, to summarize, we have this Sigma protocol that satisfy all the properties that the sequential proof requires. And then I can finally define a ring signature from it. And the idea is quite simple. So suppose that there are these three users with their public key that are, in this case, since we are this KeySign case, three super singularity curve. And they know the secret key just for one of the users, suppose the blue one. And how do I proceed to generate the signature? I generate the commitment, so the commitment curve, and then I hash it to get the challenge, but not the challenge for the blue public key, but I will get a challenge for the purple public key. And then, since like this modified KeySign protocol has the property that it's possible to simulate starting from the challenge and the public key, I will be able to get the commitment and the response for this valid transcript, commitment, challenge, and response. And then I will use this purple commitment as an input for the hash function that will be used to compute, again, the challenge, but not for the blue or for the purple one, but for the green public key. And again, since the protocol now is special only identifies zero knowledge, I can get a commitment and a response such that commit, challenge, and response are a valid transcript. And finally, I will get the challenge for the blue user by hashing the green commitment in a simple way. That's why usually you refer as ring signature. And since I actually know the secret key, given challenge and commitment, I can compute the response, and I have a valid signature. I can send all these three transcripts as a valid signature for the document and the ring. Also, note that for efficiency reasons, we can also remove all the challenges, since like they can be computed from the commitment. I just need one, and at the end, I will try essentially to check if the challenge that I get by hashing commitment, purple commitment, is equal to the challenge that I get by hashing is the challenge that I send at the start. And also, if the protocol is commitment recoverable, that means that from the response, I can get the commitment. And this is the case for the modified SQISign, since given the response isogeny, just look at the codomain to get the commitment, at the codomain of the composition between the response isogeny and the challenge isogeny to get the commitment. I can also remove all the commitments, and now the challenge will only be a string with the signature will be a string with the challenge and one response for each of the user. So the final cost of the signature will be, yes, be linear in the ring size, but the factor, like the angular coefficient of this linear polynomial will be relatively constrained, since it's just an isogeny of two isogeny. Okay, but is this like, can I imply, like, since I created this ring signature starting from a unification protocol, can I imply some properties of the ring signature from the unification protocol? Yes, I can do that. In particular, I can imply unforgeability. This is like pretty standard. And it's nice that I can imply it from minimal assumption on this verification protocol. But if I have the security against impersonation, that means that it's hard to essentially try to impersonate a valid user without knowing the secret key. I can imply unforgeability. And the idea is quite easy. So suppose that I want to impersonate the blue user, and I have an attacker against the unforgeability of the ring signature. I look inside the code of the attacker, and since there's this circular structure, at some point it must exist one committed value that has been sent to the random oracle. Assume that we are in the random oracle model. That means that the adversary to compute an hash need to send me the value you want to hash, and he has sent me the blue commitment before receiving the green challenge, the challenge from the green commitment. At this point, what I do, if I am lucky, this will happen with probability 1 over the ring size, so it's still polynomial. I will send this commitment to the challenger for the security against impersonation property. I will receive a challenge since I'm trying to impersonate the blue user. And then I will essentially reprogram the random oracle in such a way that the green commitment will return as challenge the challenge I received. And since the adversary that I am interacting with should be able to compute at some point a signature, it will pop up a valid response isogeny that I will be able to respond to the challenger. And this security against impersonation is the minimal assumption that we need to get from a verification protocol to a valid to a digital signature. And if you look inside the SQISign specification, they actually show that under the computational assumption, they have the soundness and the weak honest verified zero knowledge implies the security against impersonation. That this implies not only the security of the SQISign signature, but also the security of a ring signature built over SQISign. Okay, so we have the unforgeability. Now we need to see if the ring signature is anonymous or not. The anonymity property, as I say, I will briefly repeat myself, is essentially the property ask that if I have an adversary that is looking at a signature given a certain set ring of public key, a valid signature that actually verify, it will try to understand which one of the user is the responsible one for the signature. And there are different kind of anonymity. Let's say the weakest possible version, the adversary can only see the valid signatures and public keys, but it may also be able to see secret key. And this is called full anonymity. And as before, it's I find pretty nice that I can imply different level of anonymity if I have different assumption, different characteristic properties for the verification protocol, honest verified zero knowledge. And the reason why we would like to focus more on not on just anonymity, but also on full anonymity, is that recently several awards came up in which this property is essential. For example, it's essential for designated verifier signature, in which I try to convince, I want to send to another user a signature that is actually valid, that he can trust me on producing it, but he cannot send this signature around and show that I signed a certain document. And the core idea is essentially just produce a ring signature with two user, me and the designated verifier. Because at this point, if he tries to go around and claim that I signed this document, I can always say he may have signed it himself. And since the signature is full anonymous, even if he shows his secret key and I show mine, it should not be possible to understand if it was him cheating or me signing the document. And then there are other like construction based essentially on the same ideas and same construction that are like deniable key exchange and deniable authenticated key exchange CAM. And here I inserted some reference if you're interested. And as I was saying, now we would like to imply from property of the identification protocol, property of the ring signature. And the idea is like, if I just want to have the anonymity, that means like the adversary should not be able to distinguish, like to find the signer without the secret key, with only the public key. I want the identification protocol to be weak on verified zero knowledge. That means that the simulated transcript are indistinguishable against probabilistic polynomial time adversary that do not have access to the secret witness. And this is the case, for example, for SQISign, this for the KLPT-based one. Then there is like perfect anonymity that would be like the best possible option in which like even against unbounded adversary, it's not possible to understand who is the responsible for the signature. And this is like implied by perfect honest verified zero knowledge. That means essentially the simulated transcripts are like exactly equal, distributed in the same way as honest one. And then there is like a property that is in the middle, that is the one we are looking for, aiming for, full anonymity, that consider adversary with secret keys and require the strong unverified zero knowledge that, as you can imagine, is essentially requiring that simulated transcripts are undistinguishable from probabilistic polynomial time adversary, but given the secret keys. So as I said, we see now that SQISign falls shortly on this last property, and it's only weak on certified zero knowledge. And the reason why this is true is like hidden inside the KLPT machinery. So I will try to give you an intuition on where is the problem. This already arises like in the specification. Like you can find a reference for the fact that they know that SQISign is just weak on certified zero knowledge. As I said, it's not a problem for the signature, but now we will see in detail why it is, since we would like to make it strong on the verified zero knowledge. Okay, so let's consider like the geometric world of supersingular curve, isogeny, and endomorphism. What's happening in SQISign, in KLPT, sorry, is that I have an isogeny, EPUB, a public curve, E, linked by a secret isogeny to E0, the supersimilarity curve with J invariant 1728. I have another isogeny phi, and now I don't care about its degree. And what do? I pull it back on E0, and I consider the class defined by this isogeny. In this class, I essentially look for the shortest isogeny that I can find of prime degree. Let's call it phi L. And then with this isogeny, I essentially start to smash it very hard until I can get one that is again the same class starting from phi L, but has smooth degree. And essentially now I get an endomorphism given by the composition of phi L with the dual of sigma resp. And the morphism is just an isogeny function. And it's really a peculiar shape in such a way that when I push it through the secret isogeny, it will still be an isogeny with the same domain and condomain of phi, the one I started with. This is nice.
Giacomo, sorry, Giacomo, we
Yeah.
just lost you for a little bit, so maybe you just want to repeat like the last thing you said, like the last
Oh, sorry.
explanation. It was really just like the last sentence that you said.
Okay, so like we were at this point.
Yes, exactly. Thank you.
Okay, so I was saying that this endomorphism, that is the composition of phi L and the dual of sigma resp, has really a peculiar shape, and like it lie in a particular like structure that is called like an Eichler order. That essentially mean like in simple geometric word, this endomorphism is still an endomorphism if I push it through tau. And this means, in particular, that if I push sigma resp, and I consider its image starting from the public curve EPUB, I will get another isogeny that will end in the same, will have as codomain the same codomain of phi. And so it will be like a valid response. However, if I like look to this machinery in another way, I would like to look at what's happening in a more algebraic point. Like now, I look at the problem in a geometric way, but now we look at it in an algebraic way. And to do that, we use a tool called during corresponding, in which like to this word, we associate a quaternion word that essentially we consider a rational algebra with two additional elements, I and j, such that I squared is equal to -1 and j squared is equal to -p. And like there is a lot of magic involved here, but essentially these like deep algebraic results tell us that supersingular curves are essentially maximal order in the algebra, that are lattices that are still rings. That isogeny are ideals that links this maximal order, this like strange subset of the quaternion algebra, and endomorphism are just like element in this quaternion algebra that I will refer as quaternions. So if I look at the KLPT machinery from this point of view, now what's happening? I have two orders, the one in 0 associated to E0, and the one associated to the secret to the public curve, and I have an ideal linking them. I have another ideal that represented the isogeny phi. I compute something that is the equivalent on doing the pullback, but in the quaternion world, and get a class of equivalent ideal. Inside this class, I look like for the shortest one, and then I get like essentially by solving some like algebraic equation, by smashing this class very hard, this ideal, I get another like I get a quaternion that will lie in a very strangely shaped lattices, like in a very strangely shaped subset of this of the quaternion algebra. That it will have like nice properties. In particular, will allow me to push it and to have the degree I want. What is the problem when like I try to distinguish an isogeny, like a random isogeny, from one generated like a simulated isogeny that is just a random isogeny from one generated by this algorithm? Essentially, like suppose that I have the secret key that is the link between E0 and the public curve, and I push this curve back on E0, and I compute again the shortest isogeny between E0 and E prime, and like the first problem that I have here is that this phi L is deterministic. Like since for efficiency reason in KLPT, they need to take the shortest one, otherwise it will be like much slower. The shortest is also deterministic. There are very few short isogeny, and I can just like list them and try them all. And at this point, if I go back to the quaternion world, what I have the ideal associated to the short isogeny. I have the ideal associated to the response isogeny. And these two ideals together are an endomorphism. That means they are a quaternion. And since I was saying, like before, in KLPT, they do a lot of smashing, and they force this quaternion, like these endomorphisms, to be in this lattice. That is essentially the rotation by a known value, because like it just depends on L. I can just compute it from the norm of L. And then like it's the rotation of a really strange shaped lattice. And I can test the membership inside this lattice, because essentially what is written here, like here is written in a fancy way, but like if I write it in the standard basis, the first two coordinates of this quaternion will be a multiple of a big prime n that is a product of, sorry, a big semi-prime n. And I know this semi-prime because it just depends on the secret and on L. And I can test the membership. And like the probability of this happening for a random quaternion, for a random composition of two isogeny is essentially negligible, and so I get a pretty strong distinguisher and efficient. And like just to summarize, the problem that I encountered here were like that first of all, I have a knowledge of the secret key. That means essentially a knowledge of this strange like object that is called like Eichler order. That like his knowledge is equivalent to the knowledge of the secret key. Then I from this Eichler order I can recover the class of this of the pullback ideal. This just depends on the ideal and the Eichler order, and then that the shortest isogeny L that phi of L that I was referring for is just computed in a deterministic way starting from the class using this like equivalent prime ideal subroutine. And so since we are looking for unification protocol in which it's not possible to distinguish like simulated transcript, simulated response isogeny from the one generated from KLPT, we would like to try to re-randomize, add some kind of randomization inside KLPT in such a way that even given the secret key, that's been essentially the endomorphism ring of the public curve, I still cannot like perform this test. And the idea is essentially that I will run this randomized version of KLPT in which instead of using the let's say a standard isogeny that usually like is the shortest one for efficiency reason, I will sample a random one between all the possible isogeny between E0 and EPUB, bounded by a certain number B. And then using this random connecting isogeny, I will repeat all the structures. So I will compute the class, I will compute phi of L and phi resp, and it will still have a peculiar shape in such a way that I can push it. But like the peculiar shape that it will have strongly depend on the random ideal that I use. And this like I can see when I look at what's happening in the quaternion world, so under the during correspondence. Like more formally, in the paper, we wrote it in this way. So essentially, our new hardness assumption is that if we add this randomization step, the problem of distinguishing between simulated transcript and like an original one is equivalent to trying to perform essentially to understand if the response ideal lie or not in this set. And like this set is much bigger than the one involved in the classical SQISign because essentially there is this additional indexization that is given essentially by the random sampling of the isogeny between of the connecting isogeny. And the reason why we believe this, like clearly this is again an assumption, so it's not a formal proof. But the reason why we believe this to still be hard is that like if I am like now an attacker and I want to try to distinguish a simulated transcript from an original one, I suppose that you have an original one. What I would like to try, if I want to mimic the previous strategy, is to essentially recompute the class and then restart all the process and test if the endomorphism that I get satisfy a peculiar like structure. However, to do that, I really need to get the random ideal that was used. But this is like, since it was somewhat random, I cannot get it. And if I cannot get this random ideal, we think it's not possible to also get the class. And the reason why is that if you look at like from a geometric point of view, the reason is essentially from a, let's say, from a quaternion point of view, the reason is that I cannot like push an endomorphism and hope it to be against an endomorphism. But to see like the difficulty of this happening, I think it's easier to see it in geometric world. So suppose that I have a response isogeny. Like if it was computed in the honest way, there should exist like a random tau, a random isogeny tau, and the push of this isogeny. And what I would like to do if I want to get the class, essentially, I want to find another of this isogeny since I know all this set, but we expect this set to be like suppose that is exponentially exponentially sized, and I take another one in this set, and knowing essentially the class know essentially means that if I pull sigma through tau, I will get again another sigma second, sigma prime prime, so that it will have like the same domain and condomain of sigma resp prime. And this is essentially equivalent to asking that the push of tau through sigma resp and the push of tau zero through sigma resp is an endomorphism. So these two curves should be the same. But since like from the results in supersingularity curve you can trust, we know that like mapping isogeny to long isogeny of smooth degree, essentially we give a distribution that is statistically undistinguishable from the uniform one. The probability of these two curves being the same one, like very low. So we expect the problem of recovering like the class, even if like we have like
Did we lose Giacomo?
I think maybe so.
Oh,
Oh.
no, we lost him. Okay. I'm sure he'll be back.
Yeah.
Just 1 second.
Oh no. Well, everyone stay where you are.
Oh. Hello.
Hey.
oh. Sorry.
Okay.
Do you see me?
Yes.
Okay.
I think we lost you basically right before you switched to this slide.
Okay, perfect. So like now, under the assumption that I showed before, so that it's hard to recover the class, it's hard to recover the short isogeny. Essentially, it is hard to test if these two transcripts are undistinguishable. We have a strong, honest, verified zero knowledge protocol. And does this imply a full anonymity ring signature? We just need like now to fix some parameter and see like how bad the overhead is for this adjustment. First of all, we need to find a right bound B, and we want essentially a bound in such a way that the number of connecting isogeny of prime degree is exponential. Doing some kind of like basic estimation with Minkowski bounds, we get that the expected number of isogenies between two curves is essentially a square of this parameter, essentially b squared over p. So we can fix b to be approximately square root of p times the square root of 2 to the lambda, where lambda is the security parameter. And then from b, we can also fix the final degree for the response isogeny, that is like the most important parameter in SQISign because it will influence the final signature size. Essentially, it will be 3 log p, that is a standard term from SQISign, plus 3 log b. For example, in SQISign, we would have, instead of log b, we would have like 1/4 of log b. While in our case, essentially we have 3 times lambda over 2 plus 3 times, sorry, 3 times log p divided by 2. And so we get a final length of the curve that is like around 5.25 log p, plus clearly the term given by the log p for the correction term. This is essentially an increase of 40% with respect to the classical SQISign, that is 3.75 log p as an expected length of the final isogeny, or final 2 isogeny. And so, like, we try to run, like, to write down a proof of concept implementation and to use like the number, like the timings from the SQISign implementation in C, and we expect as a final size for the signature to be 16 plus the size of the ring times 181 bytes. And as a remark, like as a corollary, if we don't really care about the full anonymity, we can get even better, because we can just use like the standard SQISign protocol just with the commitment and public key, commitment for and public curve inverted, and we will get an even better angular coefficient for the linear growth of the ring signature. So, as a closing remark, we can even compare it to the other like full anonymous ring signature that are like based on lattices, because to my knowledge, these one are the 2 best ones, that are Gandalf, that is based on trapdoor lattices, and also dual ring, that is also based on true lattices, if I remember correctly. And essentially, we see that up to 29 user, we get the best full anonymous ring signature. And if we even drop the full anonymity, we can get the best signature up to around 40 user. So before closing, like I didn't spoke about the other part of the signature, but I just want to like quickly list the characteristics, just to, if you're interested, then yeah, surely me or Rifu or Antona can answer more. But in this case, instead, we would use the GPS signature, as I was saying, combined with calamari and falafel. Then, like in the paper, it's also like, since the GPS signature is relatively old as a scheme, and we incorporated all the possible like improvement that followable from SQISign HD West, SQISign HD, etc. And we get essentially to my knowledge, the best full anonymous logarithmic size ring signature for NIST1. Here I listed some parameter, but yeah, you can get more on the paper. So, thanks for asking. Thanks for listening, and if you have a question, feel free to ask.
Thank you very much for a great talk. Yeah, as always, you can unmute your mic or just type in the chat if you have any questions.
I'll just stop the recording. No.